Hi, and welcome to the second video of two videos for section 1.1 of Math 181 at UNLV. So in the first video for this section, we talked about the idea of functions and their domains. In this section, we're going to talk a little bit more about functions, specifically the piecewise function, as well as talking about some specific functions, as well as when a function is increasing or decreasing. The first thing we're going to look at is the piecewise function. We use piecewise functions a lot, and I mean a lot, in calculus. So it's very important to understand this concept. When we're within a specific domain, when we're talking about specific values, what does the function look like? And then as we move into a different domain, does the function change what's happening? So again, a real life example of what are we talking about with a piecewise function. So let's say that, go back to this idea of a paycheck. So in the first videos we talked about what? Somebody's making $10 an hour. So we kind of gave a graph assuming that you could make some amount of income for every hour that you worked. Well, once you hit 8 hours, what happens? So if you were making $10 an hour, when you got to 8 hours, you made how much? You had $80. But if you start working more than 8 hours, i.e. overtime, maybe you get time and a half. So what happens then? Well, then you're not making $10 an hour like you were here. Maybe you're now making $15 an hour. So what happens to the graph? It jumps from here to a higher level, keeps going at the same angle there, but because we're now making time and a half, $15 an hour, it's not a continuous graph the entire way. And then remember our notation from Math 126. If we have a closed dot, that means that's included at that point. An open dot means not included. It goes right up to that point, but that point's not actually included. So at 8 hours, we would make $80, but anything after and above that, it goes up to $15 an hour, but we want to indicate that at that point 8, that value is not included. If we colored in both circles, what would happen? We wouldn't know, are we making 80 or are we making 120? So that's why we have the notation open circle, closed circle. So let's look at an example. Let's say we have this function f, and it's notated by the following, and this is how the piecewise functions will be notated for us. 1 minus x if x, our domain, is less than or equal to 1, or x squared if x is greater than 1. Notice here, one's less than or equal, the other is just strictly greater than. We couldn't have the less than or equal, greater than or equal, because then when our value was actually 1, we wouldn't know which function we're supposed to apply. So if that's our piecewise function, there's multiple pieces to it. That's our notation. And we want to find the following. Find f of 0, f of 1, f of 2, and then finally graph this function. What does it look like? So we knew we had the graph here for this idea of the paycheck. Given this function, what would it look like? So first off, f of 0, well, this just means what? We just plug in 0 anywhere we have an x in the function. But because we have two possible functions here, we have to figure out, okay, which one of these do we use when x is 0? Well, if x is 0, that means that x is less than or equal to 1, which means we use this function here, the first one. Let's call this, we'll call this one 1, this one 2, just to keep track here. So we're going to be using function 1, so f of 0 is 1 minus x, 1 minus 0, and 1 minus 0 is 1. f of 1 is what? That means x is 1. Well, when x is 1, we're still using this first function. So 1 minus x, 1 minus 1, 1 minus 1 is 0. And then lastly, f of 2, well, when x is 2, x is greater than 1. So that means we're using now equation 2 in this case. So now we're not using 1 minus 2, we're using 2 squared. And 2 squared is 4. So that's our 3 values evaluated at those specific points, 1, 2, and 3, and how do we figure out which equation we're using. Now we have to graph it. So when it's time to graph a piecewise function, just think of it as separate problems. You want to graph this equation, then you want to graph that equation. If you have 3 or 4 or 5 pieces, fine, just graph them separately. So I'm only worried about this first equation. So if we say that f of x, remember that we can substitute back and forth. F of x is really just like y, right? If we're making a graph, it's our y value. So if I have y is equal to 1 minus x and I wanted to graph this, well, what is this? This is a graph with the, in y equals mx plus b form. My intercept is at 1. And slope is negative 1, meaning down 1 over 1. So I have a line that looks like that. My domain for this is x is less than 1, so everything all the way to infinity. So that's just going to keep going forever to the left. But it goes how far? It only goes up to 1. So I can't keep drawing this thing any further distance past 1, because then it's no longer part of the acceptable domain. But because x is less than or equal to, it actually includes 1, I would put, what? A closed circle on that part of the graph. Now, so that's for the first one. That's graph for number 1, function part number 1. For number 2, this is what? This is x squared, which is what? Is a parabola. So, my parabola would look like what? It would look something like that red dotted portion, right? But I'm not including the whole parabola. I'm only going from where? From x is greater than 1. So if I were to draw a vertical line at 1, wherever this hits, which is here, everything going off to the right. But this graph, what? It does not actually include the point where x is equal to 1. So that means what? That means I have to put an open circle at the end of the parabola there to signify that it's this parabola but not including when x equals 1. When x equals 1, I use the black line going up to the left. So that should be your graph for this piecewise function. As you can see, 2 pieces representing different values depending where we're at within our domain. What's our value of x? Then we can figure out, all right, which equation are we supposed to be using? So, recall one of our specific functions here, which is what? Which is the absolute value. So absolute value, we knew what? We had this notation, a with the bars around it. And this represented what? It was the distance from 0 to a point A on a number line. So because it's distance, that means what? It's always a positive value. I can't say I walked -3 miles. No, I just walked 3 miles, but maybe it was to the left. Thus, the -3. But if we're talking about absolute value, we're talking about the net distance, and that would be a positive value. In calculus, we are now going to represent absolute value as a piecewise function. And we will represent it as such. If I have the absolute value of a, this is just a, whatever value's inside, if a is greater than or equal to 0. So if a is 8, well, that means what? 8 is bigger than or equal to 0, so the value would just be 8, positive 8. But it's equal to negative a if a is less than 0. This is what will confuse people. Like, negative a if a is less than 0, that doesn't make much sense to me. But let's think about an actual example here. So let's say I had absolute value of -3. If I wanted to know what this actual value equaled, well, -3, my a, is less than 0. So the value that would get kicked out is what? It's negative my value for a. So -3, which is what? Positive 3. Thus, it's always generating a positive value for us, which is what we want, because our absolute value is always talking about positive values. So if we're talking about absolute value in calculus, we're talking about this piecewise function where if a or x or whatever value is in there is bigger than 0, we just take that value. If it's less than 0, we take the negative of that value, which will generate the positive value for us. Another recall notion is our idea of even and odd functions. So first we have an even function. And an even function is what? Well, an even function is one that if we plug in -x into the function and then simplify it, it just generates what? It just generates the original function back to us. So for example, if f of x is equal to x squared, and we want to know, is this an even or odd function, or maybe it's neither? What do? Well, we put in -x into our function. So f of -x means we have -x, the whole thing squared. Take -x, plug it into our function anywhere that we have a value for x, and then simplify. So this is like what? This is like -1 squared times x squared. If we break this piece apart, there's that invisible 1 in front there. So -1 squared is just positive 1. X squared is just x squared. So now that we've simplified, we can compare it to our original function because they're the same. Because f of -x is just equal to f of x, this would be an even function. How about odd? With an odd function, we do the same process. We plug in -x to the function, but what it generates is not the same thing, but it generates the negative of that function. So everywhere there was a negative sign would now be positive. Everywhere there was a positive sign would now be negative. So again, for example, let's say f of x is equal to x cubed. I want to know, is this an even or an odd or maybe none of the above type function? So if I plug in f of minus x, this becomes -x to the third power, which again, if I separate it, is -1 to the third power, x to the third power. -1 to the third power is just -1. X to the third power is just x to the third. So I end up with -x to the third. Now compare this to our original. The original was plus x to the third. Now the plus is changed to a minus. So because it switched just that value, that would tell us that this is an odd function. Let's look at some examples. And what I'll do here is I'll put these on the board. And if you want to pause the video, try them yourselves, figure out are they even, are they odd, or maybe they're none of the above. So neither. So are they even, odd, or neither? Neither means what? Well, it means that it's not the original function, it's not the negative of the original function. There's plus and minus signs different all the way through. That would give us a value of neither. So first, f of x is equal to x to the fifth plus x. The second one, g of x, is equal to 1 minus x squared. Third one, h of x, is 2x minus x squared. So go ahead, hit pause. You're using this methodology to determine it. Plug in your minus x, see if it kicks out the original negative signs throughout, or maybe none of the above. Once you've done all three, come up with an answer. Come on back, and we'll see how you guys did. All right, welcome back. So, for the first equation here, f of x is equal to x to the fifth plus x. If I want to know, is this even or odd? I'm plugging in minus x, and that would be what? Negative x to the fifth plus negative x. So again, we have that invisible 1. Negative 1 to the fifth power is negative 1, and then x to the fifth. And then plus a minus x, that means minus x. So now we go back and compare to the original. Well, the original had plus x to the fifth, now it's minus. That would indicate this might be odd. This was plus x, now it's minus, so that one switched as well. So yes, this one would definitely be an odd function. Number 2, g of x is 1 minus x squared. So here we do g of minus x. The function name is g. The important thing is here we're plugging in negative x throughout the function. There's no x here, so that just stays 1, and then minus a negative x squared. Well, again, this just stays 1. Negative x squared is what? Well, this is, so it's minus, negative 1 squared is positive 1, x squared is that, so simplifying that is 1 minus x squared. Go back and look at our original, they're the exact same, so that means what? That means this would be an even function. Lastly, number 3. So now if I have h of minus x, if I plug that in everywhere, I get what? 2 times negative x minus negative x squared. So 2 times negative x is minus 2x, and then minus, again, negative 1 squared is positive 1, x squared, so that just becomes minus an x squared. So now go back and look. This was plus 2x, it's now minus 2x, so that tells us, okay, this might be an odd function, it changed. But then what do we have here? Minus x squared, minus x squared. It's the same. That part didn't change. So that means what? This one is neither even or odd. So a little shortcut here for you to kind of notice a few things here. This first one was an odd function, right? Well, let's look at the powers here. This is the fifth power, that's odd. This is x to the first power. The first power is also odd. The powers of all of these pieces were odd, and we ended up with an odd function. How about the second one? Well, this power is 2, that's even. This one doesn't have a variable, right? So that's really like what? That's like x to the 0 power. And so in this case, even though 0 is not really even or odd, we're considering it as an even value because it's an even amount 2 away from 2. So anytime we have just a number, that's considered an even value, and then we have an even exponent here, and we ended up with an even function. And how about here? This is x to the first, that's an odd. 2 is even. So because our exponents, one is odd, one is even, what did we end up with? Neither. So it's kind of a good way for you, let's say you have a quiz or an exam in your calculus class, and you want to double check your answers. That's an easy way to kind of go back and look. All right, what's the exponents? Are they even or odd? If they're both odd, I should have ended up with an odd function. Last concept for section 1.1 is the idea of increasing and decreasing functions. If you want the algebraic definition, it's on page 7 of your book. This is one of these situations where if I wrote this thing out, it's like I have no idea what's going on here. It's a lot of words with math concepts and less than signs, equal signs, function values. I'm not sure what's going on. It's easier to think of this thing as the simple explanation is if you have the graph, is it going uphill? Well, that would be what? That would be increasing. Or is it going downhill? That would be decreasing. So basically, if we're talking about it from a function standpoint, if f of 1, if that value is equal to 3, and if f of 7 is equal to 9, well, that means what? If I was to graph this thing, 1, 3, 7, 9, I don't know what's going on in between here, but from 1 to 7, that would be increasing. It's going uphill. And that's the simple idea as far as what's going on. If we look at it in a general sense, if I had this following graph, let's say we're starting at point A, the top here is B, the bottom here is C, and the end of this graph is D. Well, from A to B, what's happening? We're having to go uphill. So that means this would be increasing from A to B. From B to C, we're going downhill. Thus, this would be decreasing between the interval B and C. And then from C to D, what's happening? Well, we're going back uphill. So again, this function would be increasing on the interval from C to D. So that's the main concept. Let's look at an example, numerical example. If f of x, our function, is equal to x squared, find where this function, where f of x is increasing and find where this function is decreasing. So let's draw this. If it's possible to draw the graphs, do it. This whole semester, calculus becomes a lot easier when you have a graph because you can actually see what's going on around that point that you're talking about. X squared is what? It's a parabola, right? With its vertex at 0. So the first thing said, where is this increasing? That means what? Where is this thing going uphill? Well, it's going uphill from where? This is 0 all the way to infinity. So because we're starting at the point 0, going to infinity, so actually let me change this one here. So at 0, is this thing increasing or decreasing? Well, neither, right? Because technically at that point it's gotten flat. That's our starting point. So we're actually going to use an open parenthesis there, open bracket, or the parenthesis, meaning it's not included. That's where it's starting, and then it's going to infinity. It's decreasing from where? It's going downhill from negative infinity, again to 0, but it's not actually at 0. It's not increasing or decreasing at 0, right? Because, as we're going to learn, this has a specific name where it changes from increasing to decreasing, and that point's not included in because it's neither. 0 is not increasing or decreasing, that's just our starting point. So we would put the parentheses there. All right, that's section 1.1. Hopefully it was kind of a refresher on a lot of the concepts. The big things from there, domain, make sure you understand domain. Piecewise function, make sure you know how to interpret a piecewise function. If you got those down, should be good for the rest of the semester. Come on back, we'll see you in the videos for section 1.2.